This is not that serious, just for fun. We are having fun, having it. Okay, so we were here. One thing that I didn't mention that I was discussing with José Antonio in the break, there is something. Remember that we have here some probability, and this and we say that this probability, in order that this first ordered approximation was valid, should be small. One of the signatures that this approximation is not appropriate, is not good at large scattering angles, apart from the deviation of the full quantum mechanical calculation. But imagine that we don't have the data, or we don't have the full quantum mechanical calculation, but you see that the probability becomes larger than 1. This probability becomes even larger than 1. So this clearly means that this first order approximation is not valid. Okay, so higher order correction. So when the first order approximation is not valid, like in this large angles region, we not necessarily have to go to the complicated quantum mechanical calculation. We can still use the semi-classical approximation, but we will have to solve the full couple equations, or we will have to include higher order effects. So before doing the complicated work of solving the full couple equation, we still have the chance of doing a perturbative approximation to the problem. So we start from the first order approximation, and we try to include corrections on top of this. This is an alternative approach, and this is in fact what many people have done in the literature. So many times we see this sentence of higher order corrections affect higher order effects in blah blah blah. This higher order mean different things depending on the context. So for example, if we start from the Coulomb excitation from the dipole term, that in principle is the dominant one when the dipole coupling is possible, then higher orders may refer to the inclusion, for example, of the quadrupole, 10, octupole, whatever. So these are corrections. This can be treated as additional corrections to our problem. This is a kind of higher orders. Also, if we start from the another meaning of this higher order, if we start from the first order approximation, then we can do a perturbative solution of the couple equation, try to get a second order approximation, and so on, but for the same lambda, for example. So these are going from the first order solution, perturbative solution, second order, and so on. So this is another meaning of these higher order effects. So you see here an example of this boron 8 Coulomb dissociation on gold target, so producing this beryllium 7 and a proton. This corresponds, we haven't given explicitly the expressions, but yesterday you saw observables of this kind. This is the what is called the longitudinal momentum distribution, this in this case of the core, of the beryllium 7. This is the momentum distribution of the core. And I don't know if, well, you have the data. I don't know if you are able to see this green line here is the first order calculation, including only the dipole term. And this first order approximation is a not too bad description of the data, but you see that the data shows some asymmetry, while this first order calculation gives some symmetric distribution. So this asymmetry is typically connected, is linked to these higher order effects. So in particular, you have here the dashed line here that is that includes the contribution of these 2 or 3 terms, so higher order effects in the expansion in terms of the decoupling potential. So instead of going only from ground state to a continuum, now we allow, for example, going from the continuum to the ground state or to another continuum state. So we iterate our couple equations. And then there is also a red line that is called here dynamic. This dynamic calculation corresponds to the solution of the full problem without making this perturbative approximation. So it's the full solution to all orders, to all order solution to the couple equations. So you see that the full solution shows this asymmetry. So this asymmetry is characteristic of this E1, E2 interference effect or higher order effects. In this case, the main effect producing this asymmetry is the interference between the dipole term and the quadrupole term. So some people have tried very hard to obtain information from the E2, from the quadrupole contribution here, the BE2, from the asymmetry, from the deviation of the symmetric shape. So you include in the calculation the E2 trying to reproduce this asymmetry. This is a second order expression of the coefficient C. So this is another example of we have been discussing. So if we iterate to second order, so remember in first order we have an expression with only the one potential in between, the V1, that resemble in some way the DWB approximation. So it was the first order. This is an expression that we have not derived in detail, but I give you here, this is the expression for the second order amplitude. It contains twice the potential. So the interpretation of this equation is that we start from the ground state, that is also illustrated here. Then we go to the Z channel that can be one excited state, but could be many possible excited states. So this represents a bunch of excited states. And then from this excited state, we go to a final state N. This final state N could be, for example, the ground state itself. So this second order equation can be used to see the effect on the elastic scattering of the excited state. So remember, in first order, when we solve in first order, our elastic scattering is determined by the aperture potential. So we have a V naught that describes the trajectory, and this is not affected by the excited state. We solve this independently of the couplings. In second order, we have an effect on the elastic scattering, or inelastic scattering, due to this second order term. So we go from ground state, we couple to this state, and then go back to the ground state. So these couplings will affect the elastic cross section. So even if we at the end measure elastic scattering, this elastic scattering will be affected by these intermediate processes. And we have seen this already many times during these weeks. For example, we can put all these complicated effects in the quantum mechanical picture in some optical model, for example. Or we can do a coupled channel calculation, including the coupling to the excited state, and see the effect on the elastic scattering. So we have seen different ways of including this. So this is in the semi-classical picture. And in second order, of course, we could go to higher orders, so third or whatever, the effect on the elastic scattering on this interaction. So this tries to represent in this picture that we start with the V naught potential, but at some point of the trajectory, the additional potential V1, the perturbation potential, produces an excitation of the system. It shakes the system, but eventually it adds a second time to bring it back to the ground state. So at the end, we measure elastic scattering. This transparency is dedicated to Jeff. This is the polarizability of the deuteron. This is an old problem. This is an example of this second order effect on Coulomb interaction. So imagine that we have a system like a deuteron that scatters by lead. So we have, if we are at very low energies, we expect this to follow the Rutherford cross section. So this ratio here that has a complicated definition, but this is essentially something that should be 1 if we are in pure scattering, elastic scattering, Rutherford scattering, sorry. If we have pure Rutherford scattering, this ratio should be 1. This is as a function of the incident energy of the deuteron. So 3 MeV, 4 MeV. The Coulomb barrier for the deuteron lead system is something around 11 MeV. So all these energies are well below the Coulomb barrier. These numbers show then the departure from Rutherford scattering, and these numbers are actually very close to 1. So at 3, 4 MeV, we have essentially Rutherford scattering. But if we make the measurement with sufficiently accuracy, we observe some departure from this Rutherford scattering. So this essentially measures at large scattering angles what is the difference between, or the ratio between the Rutherford scattering and the observed cross-section. And that is why the ratio becomes smaller than 1. So this deviation from 1 has to do with several effects. And the main effect that is producing this reduction comes from what is called the deuteron polarizability. So this deuteron polarizability is related to the fact that the deuteron is not a points particle. It has a standard distribution, and the Coulomb potential is not acting actually in the center of mass, it's acting on the proton. So this will produce some stretching of the structure of the deuteron. It will become polarized in the usual language. So the deuteron becomes polarized, and eventually it can break up. And sometimes some of this excitation, this breakup, this polarization can then act again and bring the deuteron back to the ground state, as in the slide before. So we have an excitation of the deuteron, and then goes back to the ground state. And this effect, so we put this produces a dipole moment, this electric field. So the deuteron can be thought as a sort of dipole moment. This is the polarizability acquired by a dipole moment in some electric field, and this alpha measures the polarizability of the system. So when we have a dipole in some electric field, this is the polarizability. So a magnitude that can be defined also for a deuteron, thought as a dipole, as an electric dipole, is the polarizability of the deuteron. It tells us how easy it is to distort the structure of this deuteron in the electric field. So it's possible to obtain this quantity measuring this departure, the deviation from Rutherford scattering. So at energies below the Coulomb barrier, the main deviation, as I said, comes from this Coulomb interaction. And the dominant term is the dipole Coulomb interaction. So we have the central Coulomb interaction that produces Rutherford scattering essentially, and then the next term is the dipole Coulomb interaction. And then we have the quadrupole, but it's much smaller. So we can use this expression. Yeah?
Why f to the power 4?
Yes, this was a question that I was about to make. So if we apply this complicated formula, we have V and V. In the case in which we can apply the adiabatic limit, only in this limit, this second order expression simplifies very much, and the effect of this second order amplitude can be simulated by an additional potential. So we add to the central Coulomb interaction an additional interaction, effective interaction, that takes into account this second order effect. So this is equivalent, this second order effect is equivalent of adding this term. This is only valid in this adiabatic approximation. So can anyone tell me why this has this dependence, 1 over r to the 4th power? Can you imagine what is the origin of the 4th and not 5 or 3 or 8?
2. Lambda plus 1 for Coulomb.
Yes, and you have the dipole term that was, so this is the effect of the V1, the dipole potential, acting twice. So it acts one here, it goes 1 over r squared for the dipole term, and then again, so in this adiabatic approximation one can simplify the rest of the terms appearing there, and one gets a very simple expression in which we have this polarizability parameter, this structure parameter that appears here. There is obviously a connection between this alpha and the B1 distribution. That is essentially what we are measuring, how easy it is to go from the ground state to the dipole states. So this is also a measurement of the B1 distribution, particularly the B1 distribution of low excitation energies. So by this, in this paper, what they did was to measure very accurately, very carefully, the elastic scattering of deuteron below the Coulomb barrier. This is a very challenging experiment. You have deviations of less than 1% from Rutherford scattering, so this is experimentally very, very difficult experiment. And they include the different effects that produce this deviation. So you have several lines here. So this dashed line here, for example, is the effect of the nuclear interaction, because this also produces some deviation from the Rutherford scattering, but the main deviation comes from this polarizability effect. So this is a parameter that they adjusted to reproduce the data and got this number. And this number can be obtained from a realistic structural model of the deuteron. The proton-neutron interaction is very well known nowadays, so you can do a separate calculation for the big one, from the big one obtain the alpha parameter, and actually agrees very well with this number. So this is a nice way of extracting some structural property, that is the polarizability, from a scattering experiment, from an accurate scattering experiment. Okay? But remember, this is only one limit. Actually, in this case, if you evaluate the full second order amplitude, this approximation is very good in this case. So this, in principle, remember, the adiabatic limit would be for high excitation energies, but the deuteron is bound by 2 MeV, so these 2 MeV are, in this context, are high enough for this approximation to be valid. Okay, so we are discussing different deviations from the first order calculation. So another signature of this higher order effects is related to what is referred as post-acceleration effects. So this is a measurement of a breakup of lithium-11 on lead at intermediate energies, 28 MeV per nucleon. And in this observable, they are measuring the velocity of the lithium-9 and the velocity of the neutrons, or the center of mass of the two outgoing neutrons. So at the end, we break the lithium-11, we have lithium-9 and the two neutrons. So if you manage to detect all particles, you can obtain this observable. So you get this difference in velocity. And the solid line is the prediction of this first order calculation. So the first order calculation gives a distribution that is centered at 0. So essentially the lithium-9 and the two neutrons are incident with essentially the same velocity of the velocity of the projectile. It breaks, and then they escape with also the same velocity. This was our assumption. The trajectory is not perturbed, it's not distorted by the other terms of the potential. So in the pure classical trajectory, the velocity of the three particles is the same. So we expect to have something, a situation in which all particles come out essentially with the same velocity. But this is not the case. You see that there is it is shifted experimentally to some positive value, and this means that the lithium-9 is accelerated with respect to the neutrons. So they come out with the same velocity, roughly, because they are inside the lithium-9, but when it breaks down, the lithium-9 accelerates, and the neutron continues maybe with essentially the same velocity. So this is not described with the first order approximation. One has to go to higher orders. So this is an explanation of this process, of what is going on. So we have lithium-9 that follows some trajectory described by the Coulomb potential, for example, or some classical potential. At some point, the system breaks. So what is happening is that at the distance at which this breakup happens, there is a potential energy, a Coulomb potential energy, that is given by this quantity. So imagine that this distance RBU is the distance, characteristic distance at which the breakup is taking place. So there is a potential energy of this value. Once the two neutrons are detached from lithium-9, the only object that is feeling the Coulomb interaction is the lithium-9. So after it breaks up, then the lithium-9 flies away, is repelled by the Coulomb potential, but only the lithium-9 is accelerated. The neutrons don't feel the Coulomb interaction, they just continue in their way. So this lithium-9 gains some kinetic energy that is of this order, and then is accelerated with respect to the neutrons. That is why we have this post-acceleration effect. And we don't give the details of people, for example, try to explain these kind of things by solving the full couple equations, semi-classical equations, for example, or including second order effects. So there was a lot of discussion on these kind of things, this post-acceleration, particularly in the 90s, where people were trying to understand this kind of results. This is another nice example of on how you can go beyond the first order approximation and get a result very close to the full coupled channel calculation. So this is a boron 8 on nickel reaction, and this is the angular distribution of the beryllium 7 after the breakup of the boron 8. So boron 8 breaks up. This is angular differential cross section with respect to the angle. So there is a solid line here that is a full coupled channel calculation with CDCC, with all orders, with Coulomb, nuclear, blah, blah, all the complications of the CDCC that you already have experienced on your own, and you will continue experience now. And then you have the dashed line that is a semi-classical calculation that agrees very, very well with the full calculation. But in order to get this kind of agreement, they had to include Coulomb and nuclear effects. So the trajectory is no longer given by just Coulomb interaction. You have to put also the nuclear part of the interaction. You have to include not only the dipole part, you have to include several multiples. And then you cannot solve to first order equation. You have to solve to all orders the equation. And also something that we have not discussed, because it's the same that we had before, to include the continuum in the full couple equations. So in the first order, you don't need to discretize in the continuum because you just have something that is proportional to the V1. So you don't need any discretization of the continuum. But when you solve the couple equations, in order to include the continuum states, you have to make some continuum discretization. So this is similar to the CDCC continuum discretization. So we don't discuss this here because this is exactly the same problem that we have to tackle in the CDCC method, and the solution to this problem is the same one, is to make some discretized representation of the continuum. So this is how these authors solve these equations. Okay, so this is another example of how to go beyond this first order approximation. And finally, I like to give you a few expressions that relate this Coulomb dissociation cross section with something that is also very much discussed in the literature and actually will be addressed in more detail by Pierre on Friday, I think. That is the radiative capture. You probably have read many papers that mention this radiative capture. So we have already discussed this photoabsorption cross section. So this is a picture of the photoabsorption. You have a nucleus, a bound nucleus compound that is composed of B and C, two fragments. This nucleus absorbs some photon and is excited to the continuum. So some energy above this dashed line, that is the threshold for the breakup in B and C. Goes excited to some continuum state, and so at the end we end up with two fragments, B and C. So this is photoabsorption. The name is very self-explanatory. So we have the opposite reaction is what is called the radiative capture. That is, we have two fragments, B and C, and they collide with each other, and eventually they can decay to a bound state emitting one photon. So starting with two fragments, we end up with a bound system. It can decay not necessarily to the ground state, it could be also to an excited state. So you have a cascade of gamma rays, and you detect at the end a gamma ray. So look at the energies in the two situations. So this is the kinetic energy of B and C that is measured with respect to this dashed line. That is the situation in which they are a zero relative energy. So you go to some positive energy between them, some kinetic energy. At the end, the energy of the photon will be this kinetic energy plus this difference, that is essentially the binding energy, the separation energy, that is the Q value of this process. And so the photon escapes with a larger energy compared to the incident kinetic energy. And here is the opposite. So the energy of the photon is used first to break the system and then finally to give some kinetic energy. So part of the energy of the photon is just to break the system, to reach this threshold, and then the rest of the energy is used to give some kinetic energy to the fragments. Okay? So one process and the other are related to by detail balance. I'm not sure that we have discussed about detail balance. So this is based on tiny invariance of quantum mechanical processes. So one process is the inverse of the other. So there is a relation between the radiative capture and the photoabsorption with some kinematical factors. And be careful with the energies that you have here. So this K gamma is related to the momentum of the photon. So this momentum, and then this K is related to the kinetic energy. So the kinetic energy is this here or here. So we have two energies going on that are related by the Q value of the reaction. So don't get confused with the two energies. And these J's are just the spins of the different fragments. So this quantity typically decays when we go. This radiative capture becomes very small as we decrease the energy, and this is because they have to overcome the Coulomb barrier. So as we go to smaller and smaller energies between B and C, to smaller kinetic energies, this process is hindered because they have to overcome this Coulomb barrier. So this decays typically exponentially according to this exponential. That is related to the Sommerfeld parameter. So many times, instead of referring to this quantity, that is something that decays very fast, one tries to extract from this radiative capture this exponential factor by multiplying by the positive the exponential with the positive argument, and with the hope that this quantity, that resulting quantity, is something that is, depends weakly on the energy. So we get something that goes to zero in a more or less smooth way. So this is called the astrophysical S factor. And this is a very important quantity to quantify the importance of the radiative capture. So these processes take place in astrophysical environments. So people try to get information of these reactions by measuring these radiative captures in laboratory, for example. But to simulate the conditions that you have in an environment, in an astrophysical environment, you have to go very low in energies, typically below 1 MeV or a few keV of relative energy, of kinetic energy. This is the actual energies at which these processes take place. At this energy, these cross sections are extremely small, so these processes are very difficult to measure. So now we will use the connection between these two processes to show a possible method of inferring this quantity, the radiative cross section, from the photoabsorption cross section. So this is done. Before that, let me show an example of a direct measurement of radiative capture. In this case, this is for a proton hitting on oxygen-16, producing fluorine-17 by means of this capture process. So the proton oxygen-16 with some kinetic energy, they merge and then eventually decay. The fluorine-17 has two bound states. The ground state is phi-half, excited state 1/2 plus. So this, when they combine with each other, it can decay to the ground state or to the first excited state. So the energy of the photon will be obviously different in each case. So this is a plot here of the yield of this process, the number of particles, for example, or some arbitrary units, as a function of the proton incident energy. So this is a measurement of the kinetic energy of this process. And we have two lines. The two lines correspond to the decay to the ground state, this one, and the decay to the excited state, this one. And from these yields, by introducing this exponential factor, one can obtain the astrophysical S factor for the two processes, which are these lines. So these lines, this is linear scale, this is log scale. You see that they have a much smoother behavior, so you can compare more easily with some calculations and try to extrapolate to smaller energies. So this is the idea of this of using these astrophysical factors. These vertical lines here correspond to some resonances in the fluorine-17 system. So some resonances are some specific energies in which the capture process is particularly favored. And So how can we obtain information from of this radiative capture without measuring it directly? Because this is one example in which it is possible, but in many cases it is not possible experimentally. So the idea is to measure the Coulomb breakup cross-section, and remember that we had a relation between the Coulomb breakup cross-section and the photoabsorption cross-section. We derived a relation between these two quantities. And the photoabsorption, we have just shown that it's just the inverse of the radiative capture. So by using detailed balance, you relate this quantity with the radiative capture, and from the radiative capture you extract the astrophysical factor. So you can infer information of this astrophysical factor by measuring Coulomb dissociation of, in this case, for example, fluorine 17 on some target that breaks in the Coulomb potential of a target, and from this cross-section, assuming that all these steps are valid, then one can hope to extract information on the astrophysical factor. So this is an alternative way of getting information. And this is my last slide for today. So now the rest of the morning session will be devoted to the CDCC again. So we go back to your CDCC problem. I stop this.